Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is AC power. Our objective is to examine the trinity of AC power, apparent, real, and reactive power, and learn to calculate these quantities. Alright folks, this is it. This is that irritating chupacabra I've been meaning to drag out of the thorn bushes by its forked tail and curb stomp to death in front of you for quite some time. I hope you enjoy this as much as I'm certain I will. A little bit of warm-up before we begin. So I started the Big Bad Tech channel some time ago for two reasons. One, the engineering educational community was in desperate need of my own special brand of sarcasm, and two, I was generally convinced that there is a better way to teach basic electronics. I've been teaching basic electronics for some time now, and if there is one thing I can say about AC power, is that it is the single most misunderstood topic for the simple reason that AC power is historically the single most mal-taught topic. There is a better way to teach AC power, and this is that better way. Forget everything you know or think you know about AC power and just follow along. These methods, although not endorsed by some of the truly awful textbooks and dinosaur instructors out there, will get you where you need to go with less confusion and toil on your part. This being said, you need to meet me halfway. You simply must understand complex numbers, phasor representation of AC quantities, and Ohm's law as it pertains to AC circuit analysis. If there is the slightest hesitancy on your part regarding any of these topics, go away and do not come back until you have mastered these subjects. If you feel you are among the worthy, put your hand on top of the internet and say, "Let us begin." As I'm certain you are well aware, DC power is the product of voltage times current, P equals VI. Similarly, AC power is the product of voltage times current, P of T equals V of T times I of T. It should be self-evident that given AC voltage and current are themselves time-variant properties, their resultant product, power, would also be a time-variant property. The primary difficulty with AC power lies in the somewhat complicated math necessary to derive the time-variant power expression. So, let us dispense with this math entirely, since the time-variant power expression is something of dubious utility anyway. Let's just make some observations about some hypothetical scenarios and see if any of these observations are worthy of further inspection. Consider plots of sinusoidal AC voltage across in red and sinusoidal AC current through in blue, an unknown impedance element Z. We're not given specific values, however we can assume voltage has a specific voltage peak and a corresponding effective value, VRMS, as does current have a specific current peak and a corresponding effective value, IRMS. You note the effective or RMS value is 1 over square root 2, or approximately 0.707 of the respective peak values. You'll note voltage and current have the same period and corresponding frequency, yet we don't know the specific values. There also appears to be some phase shift between voltage and current, and that current appears to be leading voltage by a certain amount. Again, we don't know the specific value of this phase shift, but it is of little concern for this hypothetical scenario. Given these plots of voltage and current, we should be able to form a general plot of power, given that instantaneous power is the product of instantaneous voltage and instantaneous current. During periods of positive voltage and positive current, power will be positive. During periods of positive voltage and negative current, power will be negative. During periods of negative voltage and negative current, power will be positive. Finally, during periods of negative voltage and positive current, power will be negative. Despite the use of general-purpose voltage and current waveforms with non-specified values, the resulting plot of power as a function of time should be revealing of several important properties. First, given the power waveform is on both sides of the horizontal axis, there appears to be periods of both positive and negative power. Given positive power is defined as an element dissipating, absorbing, or consuming power, negative power is quite obviously the opposite, being occasions in which the element is supplying, returning, or providing power. This duality implies that the element in question is slightly reactive in nature, in that at times it consumes power from the source, and at other times returns it back to the source. Second, The resultant power waveform still appears to be sinusoidal, only it's been shifted vertically. Additionally, it should be noted that the sinusoidal power waveform experiences 2 cyclical oscillations for every single oscillation of voltage and current. Therefore, the frequency of the power waveform is twice that of the voltage and current waveforms. This means loads in AC circuits, rather than experiencing steady-state power as in DC circuits, instead experience time-variant bursts of power. Given there is some phase shift between voltage and current, you'll note moments of peak positive power consumption and peak negative power supply don't necessarily line up with moments of peak voltage and peak current, but rather where the product of instantaneous voltage and instantaneous current experiences a respective maximum or minimum. Finally, despite the fact that power is a vertically shifted sinusoidal function with twice the frequency of voltage and current, it should be noted that it is symmetric in nature and can be averaged over time, where this average value can be thought of as a horizontal line running right through the middle of the vertically shifted sinusoidal power waveform. This is where it's helpful to think of the act of averaging sinusoidal waveforms as the peaks and valleys being piles of sand that can be moved and leveled. The peaks above the horizontal line of symmetry perfectly match the valleys below it. When the sand is smoothed out, we're left with a level average value. In this hypothetical scenario, our average value, whatever it might be, appears to be above the horizontal axis. This makes perfect sense given the longer and larger periods of positive power seem to outweigh the somewhat briefer and smaller periods of negative power. It can be therefore said that, over time, this load, despite experiencing regular momentary periods of negative power, on average consumes, dissipates, or absorbs a measurable amount of positive power. Think on this for a moment. We did not waste time on unnecessary mathematical analysis deriving the time-variant power function, yet our simplified hypothetical scenario allowed us to discover some very important facts about AC power. Allow me to draw your attention to these observations. Power can at times either be positive or negative, meaning at a specific moment in time, an element can either be consuming or supplying power. The nature of AC power appears to be a vertically shifted sinusoidal function with twice the frequency of voltage and current. Even though instantaneous power peaks and valleys as a function of time, the power function can be averaged over time. This average power figure is known alternatively as active, real, or true power. Real power is symbolized using the capital letter P. Real power is measured in units of watts. Moving on. Given these plots of voltage and current and the resultant plot of power, let's modify these plots ever so slightly. Given there is an observed phase shift between voltage and current, we earlier demonstrated that the power function, the product of voltage and current, momentarily experiences a period of either positive or negative power. What if we were to assume that there was no phase shift between voltage and current? This is not true for our hypothetical scenario, but it's an imagined scenario worthy of comparison and illustrative of an important point. If we assume voltage and current to be identical in magnitude and frequency, only this time in phase with one another, the resultant power product would also be a sinusoidal power function. However, this time it would be entirely above the horizontal axis, meaning power is always positive. As previously, the resultant power waveform still experiences 2 oscillations for every single oscillation of voltage and current, meaning that power function's frequency is twice that of voltage and current. Additionally, since voltage and current are assumed to be in phase with one another, note the power waveform now peaks every time voltage and current peaks. This being said, note the peak-to-peak span from the top of the power peak to the bottom of the power valley in our imagined in-phase scenario is still the same as that peak-to-peak value experienced in the actual out-of-phase scenario. This might seem counterintuitive, but it's true due to properties of sinusoidal waveforms that we'll not go into today. I know we're not employing numbers just yet, so you just have to trust me on this. I mean, really, when have I ever led you astray? Yes, there was that time I pitted you against your lazy lab partner in gladiatorial combat, but you survived, and I think we all learned something in the process. In summary, there's some similarities and important differences between the plot of power where there is a phase shift between voltage and current, versus an imagined state where there is assumed to be no phase shift between voltage and current. Really, all we've done is shifted our original plot of power upwards such that all power is assumed to be positive or above the horizontal time axis. Note this new plot of power is also symmetric in nature and can be averaged over time, where again this average value can be thought of as a horizontal line running right through the middle of the vertically shifted sinusoidal power waveform. This figure is known as the apparent power value, symbolized by a capital S, and it differs from our previously calculated real power figure P in that it assumes no phase shift between voltage and current. You note apparent power S for this occasion is larger than real power. Additionally, apparent power uses different units, notably volt amperes or VA. Let me make this most important observation. What's the difference between real and apparent power? The answer is, quite obviously, that real power accounts for periods of positive and negative power due to the phase shift between voltage and current, whereas apparent power does not. If apparent power is to be likened to an ideal scenario in which voltage and current are perfectly in phase with one another and all power is assumed to be positive, it's almost like real power is what's left over after these phase-shifted effects are accounted for. In keeping with this observation, one can think of a third type of power known as reactive power, also known as quadrature power, symbolized as a capital Q, where reactive power is that power not dissipated, but rather cyclically consumed and returned or exchanged with the power supply. Reactive power, since it differs from real and apparent power, uses different units, notably VARs, which stands for volt amperes reactive. Reactive power Q is somewhat difficult to visualize graphically. However, here's how I like to think about it. Whereas real and apparent power can be thought of as simple straight line averages running right down the middle of their respective plots, I like to think of reactive power as those periods of negative power and their matching positive periods cyclically exchanged between the circuit and source. Reactive power, if you want to think of it this way, is the degree of mismatch between apparent and real power. I'll explain the dirty mathematical details of this in a moment, but one can think of real power and reactive power quite literally as different dimensions of apparent power. We'll return to discuss this multidimensional aspect of AC power in a moment. Realize the observations made about our previous single general purpose scenario can be extended into other situations with a little difficulty. Let's explore different plots of voltage, current, and power with varying degrees of phase shift between voltage and current. See if you notice any trends regarding the relationship between apparent, real, and reactive power as it pertains to phase shift. To keep everything on the same playing field, all plots make use of voltage and current with the same magnitude and frequency, only the degree of phase shift between voltage and current is varied. Our first plots show voltage and current to be perfectly in phase with one another. The plot of power shows it to be entirely positive. Given there is no cyclical exchange of negative and positive power, it's probably safe to assume that reactive power Q is equal to 0. Given this observation, real power P, being the average of the power waveform, appears to run straight down the middle of the power waveform, as does apparent power S. In summary, when there is no phase shift between voltage and current, reactive power always equals 0, and real power equals apparent power. S equals P, and Q equals 0. Let's keep these plots alive to use as a basis of comparison for our remaining tour. Let's now examine a plot of voltage and current, where current appears to lag voltage by, let's say, 30 degrees. Again, voltage and current magnitude and frequency remain the same, only for this occasion, current appears to lag voltage by 30 degrees. This is a common scenario for slightly inductive elements. The plot of power shows power to exhibit the exact same shape, only now it briefly dips below the horizontal axis, meaning there is a cyclical exchange of a small amount of negative and positive power between the circuit and the source. It's probably safe to assume that real power has decreased and the magnitude of reactive power has increased. I'll explain the reasons behind this designation in a moment, but inductive occasions in which current lags voltage are historically designated as having positive reactive power. Given this cyclical interchange, real power, being the average of the power waveform, appears to have decreased. Apparent power for this scenario, however, remains unchanged. In summary, when current lags voltage by a small amount, apparent power remains the same, real power decreases, and reactive power magnitude increases. Let's now examine a plot of voltage and current, where current appears to lag voltage by an increased amount of, let's say, 60 degrees. Again, voltage and current magnitude remain the same, only for this occasion, current lags voltage by an increased amount of 60 degrees. This is a common scenario for elements with increased inductive natures. The plot of power shows power to exhibit the exact same shape as previously, only now it dips deeper below the horizontal axis, meaning there's a cyclical exchange of a larger amount of negative and positive power between the circuit and the source. It's probably safe to assume that real power has decreased and the magnitude of reactive power has again increased. Given this increased cyclical interchange, real power, being the average of the power waveform, appears to be even smaller than it was previously. Apparent power for this scenario remains unchanged. In summary, when current lags voltage by an increased amount, apparent power remains the same, real power decreases, and reactive power magnitude increases. Let's now examine a plot of voltage and current where current appears to lag voltage by a full 90 degrees. Again, voltage and current magnitude and frequency remain the same, only for this occasion, current lags voltage by a full 90 degrees. This is a common scenario for purely inductive elements. Reactive power, the cyclical exchange of negative and positive power between the circuit and the source, now appears to totally dominate this relationship. Given the plot of power is now zero-centered on the horizontal axis, it can be said that the real power, being the average of the power waveform, is zero. Apparent power for this scenario again remains unchanged. In summary, when current lags voltage by a full 90 degrees, apparent power remains the same, real power is zero, and reactive power magnitude equals apparent power. Let's try this same brief tour for occasions in which current increasingly leads voltage. Here's a plot of voltage and current, where current appears to lead voltage by, let's say, 30 degrees. Again, voltage and current magnitude and frequency remain the same, only for this occasion current leads voltage by 30 degrees. This is a common scenario for slightly capacitive elements. The plot of power shows power to exhibit the exact same shape as previously, only now it briefly dips below the horizontal axis, meaning there's a cyclical exchange of a small amount of negative and positive power between the circuit and the source. It's probably safe to assume that, compared to the occasion in which voltage and current are perfectly in phase with one another, real power has decreased and the magnitude of reactive power has increased. I'll explain the reasons behind this designation in a moment, but capacitive occasions in which current leads voltage are historically designated as having negative reactive power. It's for this reason I'm using the absolute value operation for the reactive power. Given this increased cyclical interchange of reactive power, real power, being the average of the power waveform, appears to be less than it was when voltage and current were perfectly in phase with one another. Apparent power for this scenario again remains unchanged. In summary, when current leads voltage by a small amount, apparent power remains the same, real power decreases, and reactive power magnitude increases. Let's now examine a plot of voltage and current, where current appears to lead voltage by an increased amount of, let's say, 60 degrees. Again, voltage and current magnitude and frequency remain the same, only for this occasion current leads voltage by an increased amount of 60 degrees. This is a common scenario for elements with increasingly capacitive natures. The plot of power shows power to exhibit the exact same shape as previously, only now it dips deeper below the horizontal axis, meaning there is a cyclical exchange of a larger amount of negative and positive power between the circuit and the source. It's probably safe to assume that the absolute value of the reactive power has again increased. Given this increased cyclical interchange of reactive power, the real power, being the average of the power waveform, appears to be even smaller than it was previously. Apparent power for this scenario remains unchanged. In summary, when current leads voltage by an increased amount, apparent power remains the same, real power decreases, and the absolute value of reactive power increases. Finally, let's now examine a plot of voltage and current, where current appears to lead voltage by a full 90 degrees. Again, voltage and current magnitude and frequency remain the same, only for this occasion current leads voltage by a full 90 degrees. This is a common scenario for purely capacitive elements. Reactive power, the cyclical exchange of negative and positive power between the circuit and the source, now appears to completely dominate this relationship. Given the plot of power is now zero-centered on the horizontal axis, it can be said that the real power, being the average of the power waveform, is zero. Apparent power for this scenario again remains unchanged. In summary, when current leads voltage by a full 90 degrees, apparent power remains the same, real power is zero, and the absolute value of reactive power equals apparent power. Now that our tour is complete, consider this collection of plots as a whole. Can you recognize the larger trends emerging? Here's a couple important takeaways. 1. For all scenarios, regardless of the phase shift between voltage and current, apparent power remains unaffected. This is kind of to be expected given the terminology employed. Apparent power is exactly that, being the amount of power an element is apparently consuming, meaning it might or might not actually be true. Apparent power does not take into account phase shift between voltage and current, and as a result, we're not getting the complete picture. This being said, it's still a good measure of the possibilities. 2. For the single occasion in which voltage and current are perfectly in phase with one another, real power P is equal to apparent power, and reactive power Q is equal to 0. S equals P, and Q equals 0. 3. For occasions in which current either leads or lags voltage by a full 90 degrees, real power P is equal to 0, and the absolute value of reactive power Q is equal to apparent power S. P equals 0, and S equals Q. 4. Arguably the most important of these takeaways. Note, as current increasingly leads or increasingly lags voltage, real power decreases and the absolute value of reactive power increases. Similarly, it can be said that as current progressively becomes more in phase with voltage, real power increases and the absolute value of reactive power decreases. And finally, because it will become an important part of our regular terminology, for occasions employing inductive elements in which current lags voltage, reactive power Q has a positive sign, and for occasions employing capacitive elements in which current leads voltage, reactive power Q has a negative sign. This is an annoying but necessary technicality, but we may as well deal with it now. Given the assumed positive and negative signs, inductive elements are sometimes said to absorb reactive power, and capacitive elements are sometimes said to supply reactive power. In my opinion, these terms absorb and supply are not really applicable to reactive power, since, as we demonstrated, reactive power is an equal and opposite exchange of power. However, they've entered our lexicon, and we're kind of stuck with them. In summary, inductive scenarios in which current lags voltage results in reactive power being positive or absorbing reactive power. Capacitive scenarios in which current leads voltage results in reactive power being negative and supplying reactive power. I don't like this any more than you, but that's the truth. Like I said, this is just an annoying technicality, and the first 4 observations should be the most revealing. By all means, pause the lecture and think on these first 4 observations. I say again, 1. For all scenarios, regardless of phase shift, apparent power magnitude S remains unaffected. 2. For the single occasion in which voltage and current are perfectly in phase with one another, real power P is equal to apparent power S, and reactive power Q is equal to 0. S equals P, and Q equals 0. 3. For occasions in which current either leads or lags voltage by a full 90 degrees, real power P is equal to 0, and the absolute value of reactive power is equal to apparent power. P equals 0 and Q equals S. Finally, and most importantly, 4. As current increasingly leads or lags voltage, real power decreases and the absolute value of reactive power increases. Similarly, it can be said that as current progressively becomes more in phase with voltage, real power P increases and the absolute value of reactive power decreases. If the thought, it's almost like phase shift is the single determining factor how apparent real and reactive power relate to one another, even remotely crossed your tiny, tiny little mind, I will grudgingly admit you are not nearly as dumb as you look. For those failing to make this connection, let me explicitly point out a very important observation. Apparent power can be allocated into either real or reactive portions where the degree of relative phase shift between current with respect to voltage determines this proportionality. I say again, apparent power can be allocated into either real or reactive portions where the degree of relative phase shift between current with respect to voltage determines the proportionality. In a scenario where there is no phase shift between voltage and current, all of apparent power is being directed towards real power, and none of it is being directed towards a reactive exchange. As the differential between voltage and current increases, a smaller portion of apparent power is directed towards real power because an increasing portion is being directed to a reactive exchange. Finally, when the differential between voltage and current reaches a full 90 degrees, either leading or lagging, none of the apparent power is being directed towards real power because all of it is being directed to the reactive exchange. One might think this as real decreases, reactive increases, and vice versa relationship to be linear, but it is far from being so simple. This being said, it's not hard given a thorough understanding of complex numbers. We'll examine the calculation specifics in a moment, but real and reactive power are quite literally different dimensions of apparent power when apparent power is expressed as a complex number, and that they respectively form the real horizontal x component and the imaginary vertical y component. Too often, older instructional methods never explicitly mention this connection and go to great, almost comical lengths to avoid discussing it in this manner. Apparent power is a complex number, and it can be resolved into its individual real and reactive components. S equals P plus or minus JQ. Note the overbar indicating S, apparent power, is in actuality a complex number where real power P is simply the real horizontal x component and reactive power Q is the imaginary vertical y component. Alternatively, apparent power can also be represented using polar format with a magnitude S. Note the lack of an overbar indicating this is a magnitude only, and a direction, which I'm calling theta S. Given our previous experience with complex numbers, you should be able to convert between these forms with little difficulty. Given the polar form of apparent power, one can determine the individual rectangular components. The real horizontal x component, in this case real power P in units of watts, is the apparent power magnitude S times the cosine of the apparent power angle, theta S. P equals S cosine theta S. The imaginary vertical y component, in this case reactive power Q in units of vars, is the apparent power magnitude S times the sine of the apparent power angle, theta S. Q equals S sine theta S. Coming at this from the other direction, given the rectangular form of apparent power, one can determine the individual polar components. The magnitude of apparent power S in units of volt amperes is the square root of the sum of the squares of the real and reactive power. S equals square root P squared plus Q squared. Finally, the apparent power angle theta S is the inverse tangent of the reactive power Q over the real power P. Theta S equals inverse tangent Q over P. We'll discuss relevant details about this angle in a moment. For now, let's just put these observations in your pocket and move on. Let's now examine the means of directly calculating AC power. As we previously demonstrated, instantaneous power is the product of instantaneous voltage times instantaneous current, which yields a time-variant power function, P of t equals V of t times I of t. Recall, we skipped the complicated math and never actually took the time to derive the time-variant power function. Don't think I'm going to bait and switch you and do this now. The time-variant power function, although an entertaining side diversion for the math nerds among you, is of dubious utility, and we demonstrated how apparent, real, and reactive power can be used instead to determine average behavior power over time. Apparent, real, and reactive power are far more important properties, and although we define them and discuss their origin, we never actually learned how to calculate them. Let's do so now. As I mentioned at the beginning of this lecture, AC power is often considered an esoteric subject by first-year electronics students for two primary reasons. One, because it's a generally hard subject, and two, it's taught poorly. Esoteric, by the way, means a subject intended for or likely to be understood by only a small number of people with a specialized knowledge or interest. Part of the reason AC power may seem so abstruse, arcane, or obscure is that there are so many different ways of calculating AC power. Do not be daunted by the variety of methods I'm about to show you. I'm suggesting that rather than being overwhelmed by this wide assortment of tools, you should instead take heart in the fact that with so many different ways of calculation at your disposal, at least one of them should be able to give you a correct result. My advice is to simply pick a handful of weapons from this veritable arsenal I am about to spill on the floor in front of you and get good at using just this handful of methods. As you gain skill and experience, you may wish to experiment with other methods or stick with what you know as long as it works. I generally divide these methods into new school and old school techniques, where a new school technique is defined as one making use of complex numbers, and an old school technique is defined as one going to great, often comical lengths to avoid using complex numbers. You'd think I'd have a degree of loyalty one way or another, but I don't for a very important reason. Both methods have drawbacks. Here's my take about the two different approaches. The new school methods making use of complex numbers are fast, efficient, and give you the correct results every single time. Additionally, there is a sense of satisfaction in seeing, quite literally, the spatial relationship of apparent, real, and reactive power. This being said, the new school techniques have two major drawbacks. One, you need to understand complex numbers. My hopes are that this isn't an issue, given we've spent an ample amount of time ground-pounding complex numbers in the previous lectures. This being said, not everybody has this skill set, and you might expect a dull and apathetic drone to simply refuse to learn something new, despite the obvious advantages. Let's hope this is not you. 2. The other drawback of the new school methods is that they require a certain setup because of a very regrettable choice in terminology. Remember when we defined inductive occasions in which current lags voltage as having positive reactive power, and capacitive occasions in which current leads voltage as having negative reactive power? Yeah, well, it turns out that that was a super bad idea, and because of this monumentally poor decision, the new school methods necessitate some active intervention on your part regarding signs. This being said, if you can just remember to account for signs, it's not a huge deal breaker. Regarding the old school methods, they are also reliable and will yield the correct results every single time. Only they do so using methods that don't fully illustrate the mechanisms behind their operation. In short, the old school methods are designed so dull and apathetic drones can get a number without understanding its origin. Let's start by examining the new school methods. Recall, DC power is the simple product of voltage and current. P equals VI. Wouldn't it be great if AC power was also the simple product of voltage and current? Well, check it out. It is. S, our complex number representing apparent power in units of volt amperes, is voltage V times current I, where voltage and current are represented as phasor equivalents. I'll explain the asterisk operation in a moment. This simplicity is oftentimes never explicitly mentioned in most electronics textbooks, and something old school methods go to great lengths to avoid. Apparent power, expressed as a complex number, is simply the product of voltage and current expressed as phasor equivalents. What does the asterisk mean? It means things aren't necessarily as simple as they might initially seem. The asterisk is the complex conjugate operation, which, if you'll recall, simply means keep the magnitude the same, but change the sign of the resultant angle. If the angle is positive, make it negative, and if it's negative, make it positive. Don't make the complex conjugate operation hard. The complex conjugate operation accounts for the unfortunate designation of reactive power for inductive occasions in which current lags voltage is positive and capacitive occasions in which current leads voltage is negative. Again, I don't like this designation any more than you do, but that's how AC power rolls. But wait, that's not all. Recall DC power can also be calculated using different time-saving methods, notably P equals I squared R and P equals V squared over R. Wouldn't it be great if AC power could also be calculated using these same time-saving methods? Well, check it out. It can. S, our complex number representing apparent power in units of volt amperes, is current squared times impedance, where current is represented as a phasor equivalent and impedance is represented as a complex number. Note the complex conjugate operation again accounts for the sign of reactive power. Similarly, S, our complex number representing apparent power in units of volt amperes, can be calculated as voltage squared divided by impedance, where voltage is represented as a phasor equivalent and the impedance represented as a complex number. Again, note the complex conjugate operation accounts for the sign of reactive power. Long story short, AC power is DC power with phasors. Really, the only twist AC power brings into this picture is the complex conjugate operation, which is really just a housekeeping technique to account for the sign of reactive power. We'll demonstrate application of these methods in a moment. Before we move on to discuss the old school methods of calculating AC power without complex numbers, allow me to point out that all of these equations are valid for one condition and one condition only. This condition being that current is referenced with respect to voltage. I say again, current through an element is referenced with respect to the voltage across it. Does current lead or lag voltage, and if so, by how much? You'd think this condition would be of minor concern, but it isn't, since it establishes a standard frame of reference for all elements regardless of their position within a larger circuit. In fact, this condition is so important it may be worthy incorporating it into our three AC power equations in the form of an important disclaimer that, if not strictly obeyed, absolutely prevents any of this magic from happening. Packaging this disclaimer as an asterisk is kind of pointless, since we're already using the asterisk as the complex conjugate operation, so let's point it out using a big, hard-to-ignore star. The star says in no uncertain terms that it will take away your birthday if you do anything other than referencing current with respect to voltage. Long story short, for the purposes of AC power calculation, absolute phase shift is of little importance, and only relative phase shift matters. I'll demonstrate the significance of this important condition in later exercises.